Hello everyone. So for our ABC assignment this week, I wanted to spend some time talking about word problems. I think they're big and scary when we see them on a test, but I want to demystify them a little bit, spend some time with tips and advice that I can give to you that'll hopefully help you throughout the course of the year and maybe even beyond. So I've chosen 3 problems. This sheet is available if you want to work these out along with me. It's available on Schoology. And these are also problems directly out of our book, as you can see up top here. So let's look at this first problem, and we'll kind of disentangle all that's going on. When I look at a word problem, I always want to read the whole thing first to try to get my head around what they're actually asking us to find. So here they tell us that the annual yield per orange tree is fairly constant at 270 pounds per tree when the number of trees per acre is 30 or fewer. For each additional tree over 30, the annual yield decreases by 3 pounds. And the reason for that is overcrowding. So what we're going to try to do here is we're going to try to express the yield per tree, the number of pounds per oranges that each tree will produce. And then in part B, we're going to try to express the total yield for the entire, orange tree grove, the entire acre. So what is very important here, what we're trying to wrap our head around is what's going on. We're trying to optimize the number of orange trees. We know that if we put too many orange trees, if we put more than 30 orange trees in this acre, that each tree will produce less, but there's kind of a sweet spot we're looking for because the amount we lose to overcrowding is less than the amount we gain from additional trees. So the most important thing here is really just going to be getting our heads around what our variables represent. So they want us to express the yield per tree as a function of the number of orange trees, but we can make some assumptions here. If we plant less than 30 trees, we're not going to increase their yield, and we're not going to increase the yield, and we're just going to have less trees with the same amount of yield. So what I like to do on a problem like this is to let X equal the number of trees over 30. All right, so any additional tree, right, will just be added to the original 30. So let's see here, express the yield per tree as a function. So per tree, Y of X will equal 270 pounds minus 3 times X. That 3 represents the decrease by 3 pounds per additional tree, right? So here, if X stands for the number of trees over 30, our yield per tree is 270 minus 3 minus X. For part B, let me label that. For part B, we are going to create another function, which is the total yield of the entire acre. Well, what that's going to represent, it's going to represent the amount of oranges per tree times the number of trees. So the total number of trees will be 30 plus X, right? And what we would do here is we would multiply these quantities together. What this would result in is a quadratic, which I have pulled here from Desmos. If we were to find the maximum value of this function right here, it will exist halfway between 90, our rightmost x-intercept, and negative 30, our left x-intercept. So the x value here will be 30, and the y value, I don't have it exactly, somewhere above 10,000 there. But what I wanted to show the graph here for is what we need to be able to do. We need to be able to understand what these coordinates are telling us, right? So the 30 tells us the ideal number of trees is 30 more than the original 30 we've built. Sorry, we've already started growing. And then the y value, whatever that is, and honestly, I don't really care for our purposes here because we're just building functions. Whatever that y value is, it's actually the total yield of the acre. So the big idea here with a problem like this, sometimes you'll see these problems referred to as revenue problems. And the reason I think them as revenue problems is that one element goes down while another element goes up. right? You can think about revenue, for selling tickets to a game or something like that, where as the price goes up, the number of people who are interested in buying tickets goes down, right? That's the same thing that's going on here. One goes up, one goes down. Let's look at another type of problem. This is number 25 from our textbook. Here we have a situation. They tell us that we have 1,000 feet of fencing to enclose a rectangular playground, and then we're going to subdivide it into two smaller playgrounds with fencing. So what they want us to do is express the area as a function of one of the dimensions x. Now the area here is just simply x times y. But right now, that is not a function of x, right? You can see we have multiple variables we're dealing with. So we need to do something to deal with this y. So what we're going to do is we're going to pull in some other information. Our total amount of fencing is going to equal all of our y's. So 1, 2, 3 y's plus 1, 2 x's plus 2x. And we actually know how much fencing we're going to use. We're going to use 1,000 feet. Now, if we want to get rid of that y in our area function, we need to solve for y in our fencing problem, what you're seeing in blue at the right. So we're going to subtract 2x and divide by 3. So y will equal 1,000 minus 2x, all divided by 3. Now, just like a problem we would see back in Algebra 1 or Algebra 2 with a system of equations, we're going to take that quantity and plug it in for x. Now, we'll have an area function as a function of a single variable. It will be x times 1,000 minus 2x over 3. This is a pretty common type of problem, and as I mentioned, it's a little bit similar to a system of equations, right? It's a little bit similar. We have to solve for one variable and plug it in to another function. Now, oftentimes what you'll see with a problem like this is they'll ask us to identify the ideal amount of, the ideal dimensions. They don't ask for it here, but we can figure it out. What we would want to do is graph this function in our y equals screen in our calculator, right? And we can keep it in the exact format we see here, right? In your y equals, you may want to use some parentheses, right? If you're in your y equals screen, you can use x, open parentheses, and if you have one of those older ones, you may want to do something like this, 1,000 minus 2x, end parentheses over 3, and the second parentheses. And what we are looking for is find the max. Now that max value is going to tell us, it's going to give us a quantity. I have it on my computer here. It's the maximum quantity is 250 and 41,667. So that coordinate tells us the ideal length of our x side of the fence here and here. And when we have that ideal length of 250, that will leave us with an area of the total playground of 41,667 square feet. So x would equal 250, and then y would have to equal, well, there's 500 remaining feet of fencing. So in order to find y, we will take we could actually, approach it like a substitution problem again. Subtract 2x, so 500 over 3, or about 167 feet. So here, what we're doing is almost setting up two equations to solve for two unknowns. It's a little bit more complicated than that. The function we create isn't, linear. It's in this case, it was again quadratic. We're going to look at one more problem, and this is a problem that exists on the coordinate plane. Here they tell us that we have a rectangle with two vertices on a semicircle, and that semicircle has an equation related to it. Y equals the square root of 9 minus x squared. This semicircle also, we can see that it has a radius of 3, And they want us to find the area of this shaded rectangle. Well, I know that the area of this rectangle is going to be, well, the height of it is y, and the width of this rectangle is 2x. So I need to express this area as a function of x. This, what we have right now is not a function of x because it contains that y. Luckily, we know what y equals, right? We have a direct substitution here for for our y value that'll help us find the area. Area as a function of x will equal y, which is the square root of 9 minus x squared times 2x. Now we've created a function. We've eliminated one of our variables. Now our perimeter, we're going to approach a little bit differently. We know that our perimeter is going to be 4x plus 2y, and they want us to represent this as a function of x, p of x. Again, we're going to use the same y variable. In this case, our perimeter as a function of x will be 4x. That's fine. We're okay using x. Plus 2 times y. Instead of using y, we're going to use 9 minus x squared. So that is how we will build here. Key things to take away, we should always know what our variables represent. If you have a function of x, you should be able to tell me exactly what x represents. If you have a function containing if you have an equation involving two variables, it's highly likely that you're going to have to solve for one of those variables and plug in to a separate equation. If you're approaching a problem like 44 or like 25, where you just have a single equation, you're going to hit a dead end. So you want to find a related equation, right? Use all the information in the problem to make sense of it. I think we'll pause there. What you're going to work on next is those 4 additional problems that I've posted and given to you as a worksheet. Thanks, everybody.